Okay, so what are the or what is the criteria that we use here? It's basically, well, I put it here. It's the angle. There are three different criteria that we have to show that the triangles are similar, but the other two are used when we have like numerical problems, but when we have proofs, we only use angle similarity criteria. So let's look at the information that we have. Let me just read one more time. Given AD and BC intersect at E and AB is parallel to CD, prove that triangle AVE is similar to triangle DCE. Remember that this symbol is not a congruent, it's similar because obviously the triangles are not congruent, they are different size and they're similar. Well, that is what we're trying to prove. We're trying to prove that they are similar. So what do we know? Let's say, Daniela, what do we know? What can we mark here on the diagram? Yes. Okay, I hope you did not forget how to mark. We mark parallel lines with arrows. And what can we get with those parallel lines? Um, Giovanna, any idea? What can we get from those two parallel lines, from the fact that we have parallel lines? Remember that we're trying to get two pairs of congruent angles. That's the only thing that we need. Yes, so angle D is congruent to angle A. What's the reason? Same side interior angles. No, actually, you're mixing two things because same side are two angles that are on the same side of the transversal. These are actually on opposite sides of the transversal. They are called alternating two angles are congruent, not same side. Simply alternating two angles are congruent. So that will be the reason. So we already have one pair of congruent angles. Where is another one? Yes, angle C and angle B. For the same reason, they are alternating angles. Or you could have used the vertical angles here at E. Yeah, you only need two. You don't need all of them, three. Although if you have two angles, two pairs of angles that are congruent, the third pair is also automatically congruent, but you don't really need to say that. That's why we only use two, because the third one is automatically congruent. So we're ready. We already have angle, so we are ready for the proof. Let's start with our statements. And the reasons. We start with what we have at the beginning. So let's say, I'm putting the first one first. So let's just keep this one since I already started writing. So, and we could separate those or we could put them together. So let me put this one. Let me just rewrite it because I want it to be clear. So AB is parallel to CD. And what's the reason for number one? Yes, that was given to you. We did not get it from anywhere else. It's there given to you. What about the reason for number two? Yes, that's also given. It's right there, given to you. Now we're gonna get something from the given, so the reason is not gonna be given anymore. Let's say, Daniela, what can we put in number three? Which is already in our diagram. Mm-hmm. Yes, and the reason would be alternate interior angles. What else? What do we know about alternate interior angles? What are we saying? They are, yes, are congruent. Don't leave it incomplete. Just put it, what about alternate interior angles? They are congruent. That's what we are saying here. So Giovanna, what can we say next? Okay, I'm gonna put it here in the same statement because the reason number 3 would also apply to that, and that's what would allow me to put that on the same statement. So angle C is congruent to angle B, so they are both under the same reason. And what can we put next? Okay, so yes, because we have the angle, so one of you mentioned the angle, and now that we have the angle, now we can actually get to our conclusion, we can write our conclusion. So because we have angle, now we say our conclusion, which is to prove that triangle AVE is similar to triangle DCE, and that is because of the angle similarity criteria. I'm going to be specific here, similarity criteria, because now we have a criteria for similarity as well as for congruence, so I just want to be specific here. Okay, and so we're done. We got to our conclusion, which is to prove that triangle AVE is similar to triangle DCE, and that's what we have here, and that's the end of the proof. So let's see if we have any questions here. Any questions? Okay, so number 2. Oh no, we haven't finished yet because this question has actually another part of it here. It says, what similarity transformations map triangle ABE onto triangle DCE? What transformations would take us from triangle ABE onto triangle CDE? What can we do to get from this triangle to the other one? Any ideas? Well, I'm gonna say it then for the first one. So basically, we're getting from big to a small. Look at how we are starting from the big one, ABE. We're getting from the big to the small, and we're also changing the position. We're going from here to here. So what allows us to get from big to a small? Let's say we make first this triangle smaller, and then we move here. What transformation allow us to go from something big to something small? And let me just mention the transformations. The transformations are reflections, rotations, translations, dilations. Dilations is the only one that changes the side, because reflections, rotations, and translations, they are rigid motions, so that means the size stays the same. So let's say we dilate this one to make it smaller. Let's say like this. And then now we move this little thing, this little triangle, to where let's say the final position is. Now, what transformation would allow us to move from the green triangle to the final position? It depends on where do you reflect. Where do you reflect? That would be the faster way. Definitely, you just move from here to here, and that would actually be probably not a 90-degree, but a 180-degree, because right now our B would be here, which would correspond to our C over here. So it's going from here to here, which is forming an angle here over 180 degrees. So a rotation over 180 degrees on this point E. That's what we need. Or you could do different ways. You could reflect on, let's say, on BE. If you reflect on BE, you will get something like this. So the triangle would be here. And then you could reflect on ED, and that's how you get here. But the faster way would be just to rotate. So let's say that over here. Okay, so we did two things. We dilation, followed by a 180-degree rotation. Or you could do the other way. You could rotate first and then dilate to make it smaller. There are different answers here. Any questions? Okay. So let's go to the following one. Let's have Daniela read number 2. No, it's perpendicular. Okay, so let's first start with the first given over here. What does it mean? Let's say, Giovanna, what does it mean, this one? What can we get from this? Perpendicular. Okay, so we're going to mark it. BS is perpendicular to DB. So at the intersection of these two, we have right angles. So right angle here and here. Okay. So we also have that angle 1 is congruent to angle B right there. What can we say now? Do we have everything to say that they are similar? Because in order to prove that they are similar, we need angle. Do we have that? We're trying to prove that this triangle TSB is similar to this triangle which is in red, BSB. So are they similar? Do we have everything to say that they're similar? Yes, yes, we already have two pairs of congruent angles, so we're just going to mention, just remember this one, when you have perpendicular lines, you have to say that you have right angles, and then you're going to say that we have congruent angles. So it's like 3 steps with this one. So let's start with statements. And the reasons. Start number 1. Giovanna, what would you like to put in number 1? Okay. So I'm just going to put that. What's the reason? Okay. So now, what can you say next? You could do that. Let's do that. Let's do that. But I generally like to list, like, if there is a conclusion from number 1, if you get something, why not list it right next to it? But you could also do, you could also put this one. So let me put it over there. Angle 1 is congruent to angle B. And what's the reason for that? Yes. So now, if you were avoiding this, like, complex step, now you're going to have to go back to it. So now from number 2, you don't have any conclusion, that's it. But from number 1, there is something that you get, so now you have to say it now because there's no other option. Okay, now only before saying they are congruent, yes, they're congruent, but that's going to be said in step number 4. So let's say, I'm going to put that what you said here, but I'm going to put it in step number 4. And hopefully you can see why I put it here. So its angle BST angle BST is congruent to angle BSB. And what would be the reason? What's the reason? Why are they congruent? And if you cannot give me a reason, it's probably because you are missing one step. Why are they congruent? Well, they are congruent because they are right angles, and all right angles are congruent. There's a theorem that says that all right angles are congruent. So you are saying, I have right angles that are congruent, but you never mention that you have right angles. You're just saying, okay, I have right angles that are congruent, but you never mention that, and that's what you're missing here. You have to mention that you have right angles first. So first we're going to say that these angles are right angles. So angle BST and angle BSB are right angles. And now you can say, because they are right angles, they're congruent, because all right angles are congruent. So what's the reason for number 3? Why do we say that those angles are right angles? Yeah, it's actually connected to number 1. That's why when there is a conclusion that you can get from a given, I like to put everything together because these are all connected. So yes, it's because we're using the definition of perpendicular lines, or you could name it perpendicular lines form right angles. Okay. So what's number 5? Who can give me number 5? Yes, triangle TSB is similar to triangle PSB, and the reason is yes. Okay, so those are the proofs, and we're just going to answer the question that we have related to this one. Again, the question at the bottom says the same thing. What similarity transformations map triangle PSB onto triangle TSB? So we're going now from the little one to the big one. What can we do? Okay, so stretch, that means make it bigger, that means dilate it. So we're using a dilation. And what else? You could take this little one, make it big, like here, and then you need to move it here. How can we move this here? So let's say you stretch it to make it the size of the new one. Okay, that's not looking good. Hold on. Okay, so let's say this is the new triangle. Where do you want to reflect? On which line? SB. Okay, so if you reflect on this line, what's going to happen is that this point, which is up here, is going to be reflected on the other side of SB, the same distance. So let's say somewhere over here. This is where this point, let's call it, I don't know, let's call it X. So this is going to come here. And that's not what you have. And then you're going to connect this over here like that. And that's how a reflection is going to look. So it's not a reflection on SB. Okay, look at what happens with the triangle. It basically, it's here. It's here. And the only thing that you have to do is turn around so that this point, which I called previously X, comes where B is, and this point goes where T is, and the S actually stays the same place. So we're just taking this and moving it around. Like this piece, this point moves where T is, and this one moves where B is. So it's not a reflection, it's just a rotation. How many degrees can we rotate? Should we rotate? Yes, it's 90 degrees because, again, this point is just going to come here, and you can see over here the angles are actually there. So it's 90 degrees. So that's what we do here. And again, you could do first the dilation and then the rotation, or you could do the rotation first and then the dilation. It will be the same result. So let's put over here dilation followed by a 90-degree rotation. The rotation in this case was clockwise, because we cannot go counterclockwise if we do first the dilation. In the other one, in number 1, was a 180-degree rotation, so it doesn't matter whether it is clockwise or counterclockwise, it will get to the same place. Any questions with number 2? Okay, so let's go to number 3, which are not proofs anymore. I'm sure you saw it already. It's just problems, numerical problems with similar triangles. Let me make it bigger if it works, because this thing works sometimes and it doesn't work another time. Okay, so it seems like it's working. Okay, so here we are, that's number 3. And can I have Daniela read, please? Okay, it's only perpendicular, not bisector. It's only perpendicular. If it passes exactly through the middle of the segment, it would be a bisector, but we don't know that, or you can see here that, for example, EV is just perpendicular to AC, it's not bisecting AC because these parts are not equal. So it's just perpendicular. That symbol is just for perpendicular. So they're perpendicular. Okay, so it's already actually here marked for you. What does it mean? EB perpendicular to AC, it creates a right angle. DC perpendicular to AC, it creates another right angle. So the question is, or actually it's not a question, it's basically telling you that they are already similar. Your job is to explain why these two triangles are similar, why triangle ABE is similar to triangle ACD. Why are they similar? Because they are similar. And today we're only working with angle criteria. You already have one pair of angles here that are congruent. Where is the other pair of angles? Any ideas? No, nobody sees it? Okay, it's fine. Just tell us and see if you're right or not. Okay, those are the right angles. Yes, that's correct. And what else? Which angle? Okay, so we agree that the right angles are congruent, right? At least on that we agree, yes? So we already have one pair of congruent angles. Now the question is, where is the other one? What if you separate these two triangles? This is the little one, which is ABE, and the big one, which is ADC. If you separate them, what do you see in common? Do they have? Absolutely. Both of them are sharing angle A. So let me see if I can move this up. So if I separate these two triangles, so basically you can get this small triangle, which is more or less like this, which is this A, B, and E, and the big triangle, which is like this. It also has A, so they have the same angle over there. So this angle is congruent to itself. This is D, and this is C, but they share the same angle. So right there, it's the second pair of angles that we were looking for. So we already have angle, angle. So explain why triangle ABE is similar to triangle ACE. You could say because the triangles satisfy the angle-angle similarity criteria, or because we have the angle-angle similarity criteria. So because we have the angle-angle similarity criteria, then we could mention angle that will be angle EBA is congruent to angle DCA, and angle A is congruent to itself, which is angle A. We can always elaborate more. You could say why are they equal? Why are they congruent? Because we have right angles that are equal, because this would be for the reflexive property, because they're sharing the same angle. Any questions? Okay, I'm just writing because I think it could be acceptable in a regions, for example. Otherwise, you could just say triangle ABE is similar to triangle ACE, ACD because, but at least that's fine. And now we need to find the length that we're missing, which is the length of CD, which is here, and the length of ED, which is here, the Y. So now that we have actually these triangles separated, they could be very useful for us. We have here, how much is AB? Yes, that's 15. How much is AE? Yes, and BE is, yes. So now how much is from A to C? Very good, because we're adding 15 plus 7.5. This part we do not know, and this part here would be y plus 17, because we're also adding these two pieces, y and the 17, so it will be y plus 17. So that's how we will represent from A to D. And now using what we learned about similar triangles and actually any similar figures have sides that are proportional. So you could set up a proportion to find the missing side. So for example, if you want to find, let's say, DC or CD, you could use a proportion. And for example, we know the 15 corresponds to 22.5, so we could say 15 over 22.5, and then we have the 8 that corresponds to the x, and you solve that proportion. We're not gonna solve it because it's actually the time is over. And then if you want to find the y, you can again use 15 over 70 over 22.5. We always use the information that is already known to us, that was given, and then 17 with the y plus 17. So you cross multiply, solve the proportion, find each of the values. So we're going to stop right here. The other one is very similar to this problem. You have to explain why are they similar, and then use proportions to find any sides. So I'm going to see you tomorrow. Please try to open the account if you don't have it, the Delta Math account. And if you do have it, start working on homework number 1. Okay? Okay.